The SIR model. The SIR model is a simple model of an epidemic of an infectious disease in a large population. We assume the population consists of three types of individuals, whose numbers are denoted by the letters S, I, and R, which is why it's called the SIR model. All of these are a function of time, and they change according to a system of differential equations.
S is equal to the number or percent of the population that is susceptible. I represents the number or percent of the population that is infected. R represents the number or percent of the population that is dead or immune. Gamma is the rate constant at which people become dead or immune. Beta is the rate constant at which the infection spreads. The rate of change for the number of susceptibles is -1 times the rate constant for new infections times the number of infected people times the number of susceptible people. This is negative because the number of susceptibles is always decreasing. The rate of change of the number of people who are removed is equal to the rate at which people become removed times the number of infected. Therefore, the rate at which the number of infected changes is equal to the rate at which the number of susceptibles is changing minus the rate at which the number of infected is changing. The total population is equal to the sum of the three categories, so the total population is constant. Therefore, di dt plus dr dt plus ds dt must always be equal to 0.
To answer the questions we've been given, we have to solve for I and S. We're going to start by solving for I. Using multivariable calculus, we know that di over ds equals di dt over ds dt. This is equal to beta is minus gamma I over negative beta is. This simplifies to gamma over beta times s minus 1. Now to solve for I, we only need to integrate both sides. This comes out to be infected equals gamma over beta times natural log of s minus s plus c. C is going to depend on what our pre-constraints are. In a generic equation, C is going to equal I of 0 minus gamma over beta times natural log of s of 0 plus s of 0. To answer questions, we're also going to need to know what I's long-term value is. This will always be when I equals 0, because then we'll have a final number of removed, which is the number of dead, and a final number of susceptible, which is the number of alive, when the disease has run its course. Now the only variable we have left to solve for is s. If we're trying to find the long-term value, we know that I already equals 0. So we are left with the equation of gamma over beta, natural log of s minus s plus c equals 0. From there, we can subtract c from both sides and then pull out a gamma over beta on both sides. So we're left after that with natural log of s minus s times beta over gamma equals negative c beta over gamma. From there, we have our logarithmic rules that knows that natural log of e is the same thing as 1. So we can do natural log of s plus natural log of e to the negative s beta over gamma equals natural log of e to the negative c beta over gamma. From there, we can combine the logarithms and know that because we're adding the logs, it's multiplying within the parentheses. So we have natural log of s times e to the negative s beta over gamma equals natural log of e to the negative c beta over gamma. Now we can drop the natural logs and we'll get s times e to the negative s beta over gamma equals e to the negative c beta over gamma. From there, you can multiply both sides by negative beta over gamma. And now we're at a place that we can use the Lambert-W function. The Lambert-W function is how to solve equations when you have s and e to the s on one side of the equation, as we do on the left side, as shown above. The Lambert-W function states that x equals function w of x times e to the function w of x. So knowing this, we can look at the equation and we have negative beta s over y right here at times e to the negative s beta over y. That's how we got our functions. So we can pull that down and we end up taking that out and it's just going to be negative beta over y times s on your left-hand side. On your right-hand side, we're going to be doing the opposite, that we already have the negative beta over gamma and the negative beta over gamma, but now we have a c. So we're going to be taking the Lambert-W function of all of that and keep it exactly as it was written. When we get to this point, we want to solve for strictly y, so you can multiply both sides by negative gamma over beta. So our final answer is going to be S equals negative gamma over beta times the Lambert W function of negative beta over gamma times e to the negative c beta over gamma.
All right, so I'm going to talk about the propagation of the epidemic, which means whether or not this value is going to be large and positive, which will send your epidemic spiraling out of control and kill all of you, or if it's going to be small and negative, which will cause the population of infected people to return to a normal rate and nobody dies, which is never any fun. So, let's get started. These two equations are inversely related. So if this one is positive, this one is negative. So for the epidemic to propagate, this value, this rate has to be negative. So then this will be positive. And the more negative that this is, the more positive that is. So we want a really negative rate for this to kill everybody. So for that to happen, you have to have a less than 1 value here. So if BS is greater beta susceptibles. So if beta susceptibles is greater than your rate constant of removal, then this will be a less than 1 value, and you subtract 1 and you get a very negative number. So because these two are inverse, you'll get a very positive number. And that works because we have the i's in both parts of this. So it's basically beta susceptibles minus the rate constant of removal is what we're looking at in terms of this, determining the size and the positive / negative value of it. So when this is bigger than that, you're going to get a very high DIDT, which means your epidemic is going to take off. Inversely, if this is a lot bigger than that, then your DIDT is going to be negative and your epidemic isn't going to take off.
Now we are going to change a few variables and apply this to the zombie apocalypse, which is a slightly different kind of virus, meaning that we have to add some variables while we keep some the same. The variables we keep the same will be beta, S, and R, while we change the variable I to Z for zombified. Alpha will now represent the rate constant of zombies dying, and Q will represent the rate constant of dead coming back to life as zombies. Our new equations will then be as follows. The rate at which the susceptible population changes will stay the same. The rate at which the zombified population changes will now consist of the rate at which susceptible become zombies plus the rate at which the dead become zombies. The rate at which the dead population or removed population changes will now consist of the rate at which the zombies become dead less the rate the zombies come back to life.
Alright, so now I'm going to talk about some fallacies in the equation where it doesn't really work out because it doesn't account for some of these things. So we have our rate of susceptibles change here, but it doesn't really account for the change in population of the Earth. So this is given a constant population of susceptibles, but if you account for dPdt, where P equals population, which accounts for the birth rate and the death rate of natural death rate, not getting eaten by zombies or anything, then you had a whole new factor to the change in susceptibles because you're going to have to add in your change in population over time to find your actual rate of change in susceptibles over time. Also, it doesn't really account for total removal. It really only accounts for removal via being eaten by zombies. So if you were either immune to the disease or you became a zombie and then somebody cut you up into a whole bunch of really small pieces and distributed you across the world or something like that, so then the zombie can't reform or come back from the dead, then you would have a total removal, which it doesn't account for in our removal equation, which is dr dt equals alpha sz minus qr. And that really only accounts for the zombies coming back to life and the zombies being killed. So then it doesn't have any factor for natural death where you aren't becoming a zombie or where the zombie is shot into space or something and can't come. So now let's look at zombies. In the zombie part, our rate of zombies over time is this equation, and notice that this is a plus. So there really isn't a minus part to this. Therefore, there is no way, because we have R and then we have this, but the rate of removal is when the zombies come back. So this is going to be big and this is going to be big, and no matter what, the zombies take over the world.
Using all of these variables, we're going to answer the following questions. First, suppose we start with a population of almost all susceptibles plus a small number of infectives. Will the number of infectives increase substantially, producing an epidemic, or will the disease fizzle out? Then, assuming there is an epidemic, how will it end? Will there still be any susceptibles left when it is over, or will they all be dead? And finally, how long will the epidemic last? To answer these questions, we created a graph to simulate the conditions. Go.
So we graphed the amount of humans, zombies, and dead over time with the equations that we had. We started up with 99% of the population is human, and 1% of the population is zombies, leaving 0 dead to begin with. Now, as time went on from 0 to 100 days, you can see that the amount of humans went down and decreased to 0 when the amount of zombies ended up being the entire population. The dead, however, originally went up with the zombies being killed, but then slowly decreased, meaning the dead can go back and turn into zombies at a 0.2 rate, meaning that's what IQ equaled. Here's the spreadsheet we used to be able to make the chart. Now if we want to change some of the variables, we can. So for instance, if we started with 1% of the population dead and 0% of the population zombies, we can see exactly where the society ends up over time. So if I go over to the chart and we can see what happens.
You're pretty much still all screwed.
If I die young, bury me in satin, lay me down on a bed of roses, sink